In today's lesson, we are going to describe the end behavior and extrema on graphs. So first, I'm just going to sketch a graph, and I'm going to sketch exponential decay. So we'll come down like this. So a function we're familiar with from previous courses, and we are describing end behavior. So what is happening at the ends of our graph? Where is our graph going? And the way we do this, we're looking as x approaches infinity and as x approaches negative infinity. And our goal is to describe what's happening with our y values. So as x values are going towards infinity, what's happening to the y values? They are getting closer and closer to this horizontal asymptote. So it's getting closer and closer to 0. So these little arrows stands for the word approaches. As x approaches infinity, y approaches 0. Okay, so if x approaches negative infinity, we're going left. Well, the y values are going up. Y values are approaching infinity. Okay, let's look at another one. This will be a polynomial function. So another graph you're familiar with. Describe the end behavior of this graph. So once again, as x approaches infinity, so as we're going right, what's happening to the y values? They are also approaching infinity. Y approaches infinity. And then as x values approach negative infinity, so as we're going left, where are the y values going? They're going down. They're also approaching negative infinity. All right, let's look at a graph of a rational function. So we've been graphing these where we have maybe a vertical asymptote and a horizontal asymptote. And then we have, just doing a quick sketch, graph that looks like this and like this. Okay, so what we have to remember is we're looking at this graph at its end behavior. So as x approaches infinity and x approaches negative infinity. So where is that? It's as x approaches far right and far left. So some students get held up on what's happening in the middle of our graph. In this part, it does not matter because we only want to know what are the y values as x approaches infinity. Well, you're approaching a horizontal asymptote. So as x approaches infinity, your y values are approaching that horizontal asymptote. In this case is 3. And then as x approaches negative infinity, it's also approaching that same asymptote. Y is also approaching 3. They're approaching 3 from this one's approaching it from the top and this one's approaching it from the bottom, but they're still both approaching that horizontal asymptote. All right, another graph. You guys have not graphed this type of function yet. You will later this year. It's kind of similar to this rational function, but now there's something going on in the middle. And let's say we have a horizontal asymptote here. And we've got something like this. So sometimes we have graphs that are quite complicated, but again, we're still only looking at end behavior. So, oops, I didn't mean to erase that. End behavior is only as x approaches positive and negative infinity. So again, none of this stuff in the middle matters. We only care as x approaches infinity, what are the y values approaching? So way out here, as x is going towards infinity, again, we have it's approaching the horizontal asymptote 1. And then same thing here, as x approaches negative infinity, y is also approaching 1. Later on this year, we will be answering these same questions, but without looking at a graph. We'll be able to just look at the functions and be able to answer these questions. Okay, now we're switching gears a little bit. We're not looking at end behavior, but we're looking at certain special points on a graph. And it's your relative and absolute extrema. They're also referred to as points of inflection. So we're going to do a few things, all referring back to this function. Negative x to the fourth plus 5x squared plus 2x. So here I did just a quick sketch of that function. I don't need to be super exact right now, but do your best to make it look good. So the idea of extrema would be like the highest or lowest point. If you want the full definition, an absolute extrema would be the greatest or least value over the entire domain. So if you look at this graph, this right here is the top point. That is called an absolute maximum point. And because these go down forever, there is no absolute minimum. But now, what is going on here? It's reaching a maximum, coming back down. It's wherever we're changing directions, that is your relative extrema. So that definition, it's the greatest or least value within a certain interval. Now, I'm going to show you how to find those exact points, the relative extrema and absolute extrema, on your graphing calculator. So just watch for now. We'll spend time going over it in class, but I put in my function in my y equals. Zoom 6, I'm just getting that standard window, and I'm graphing it. Now you can calculate that second trace, and now see minimum, maximum. I'm going to do maximum and go to my max. But notice how it says left bound. Pick a spot left of the max and hit enter. Right bound, pick a point right of it, hit enter. And then you have to enter one more time. And then right there, you get your maximum value, your absolute max. So now you can do that same process to find your relative extrema. This is still a maximum, and then you go in and you find a minimum. So that's using second trace. And you can find those. You just have to do left bound, right bound, and then guess. So I'm going to give you those values, the relative max and the relative min. But maybe pause the video and try it on your own quick and see if you can get the same numbers that I got. But the relative max, this point right there, you should get negative 1.47, 3.20. And the relative min right there, you should get negative 0.20 and negative, 0.20, same x and y value. So I know that's a lot of information, but there's your full video on describing end behavior of functions and then finding those points of inflection, relative, and absolute extrema. Good luck with your lesson.